Hello, in this lecture we'll listen to two questions. On both questions we find out the area of the shaded region. So we start with the first question. In the drawing we have this big quarter circle AOB. Inside this big quarter circle we have this semicircle and this small quarter circle. Again, our task is to find out the size of this shaded area. We also know that AO equals to 10 units in its length. That is to say, the radius of this big quarter circle AOB equals to 10. OB or BO is also the radius of this quarter circle. Therefore, it is equal to 10. BO equals to 10. We define the center of this semicircle. This point is point C. OB is also the diameter of this semicircle. So the diameter of this semicircle OB is 10, and therefore the radius CB must be equal to 5. The radius CO of this semicircle must be equal to half of the diameter, that is 10 over 2, that is 5. So CQ also equals to 5. ABO is a big quarter circle, and therefore this is a right angle. This is also a quarter circle, and therefore this is a right angle. We define the touching point between this small quarter circle and this big quarter circle. This point is point P. We define this point is point Q. We define this point as point S. We define the radius of this small quarter circle as x. So QP is the radius of this quarter circle, that is equals to x. And we have those two shapes, that is to say, the semicircle and this small quarter circle touch each other externally at this point. So we define this point, that is their touching point, is point M. Repeat again that this is the small quarter circle. The small quarter circle touch this big semicircle at point M. So they have an external edge between them at point M. And therefore we can implement rule 10. On rule 10, according to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes for their touching point. In the drawing you have those two circles that touch each other externally in this point, point P. The center of this circle is at point O. The center of this circle is at point M. And the straight line that connects their centers together is of course the straight line OM. And according to this rule 10, the straight line OM must pass for point P, that is their touching point. Again, the straight line OM must pass for point P, that is their touching point. OPM is one straight line. Again, OPM is one straight line according to this rule 10. So we can actually implement rule 10 in our drawing. In our drawing, those two shapes and the external between them is point M. So they touch each other externally at point M. The center of this small quarter circle is at point Q. The center of this big semicircle is at point C. The straight line that connects the centers together is of course the straight line CQ. And this straight line CQ must pass from point M, that is their touching point according to rule 10. Or CMQ is one straight line. Again, CMQ is one straight line according to rule 10. So we join point C and Q together by a straight line, And the third line CQ must pass for point M, that is the attaching point, according to rule 10. From the drawing, it is very easy to see that indeed the third line CQ passes for point M, that is the attaching point, exactly according to rule 10. Because of the fact that CMQ is one third line, it means that CQ in total must be equal to CM plus MQ. Again, CQ in total must be equal to CM plus MQ. So CQ in total equals to CM. CM is the radius of this semicircle, that equals to 5. Plus MQ. MQ is the radius of this small quarter circle, that equals to X, according to our definition. So MQ equals to X. So in total, CQ equals to X plus 5. CQ equals to X plus 5 because CMQ is one third line. So CQ equals to X plus 5. Okay, now. In the next step, we will implement the Pythagoras theorem on this right angle triangle CQO. So copy this right angle CQO in the new equation. We will implement on it the Pythagoras theorem. According to the Pythagoras theorem, in a right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. CO is the radius of this semicircle that equals to 5. We just right now found out that the hypotenuse CQ equals to X plus 5. And QO is the missing side, so leave it as it is. Here by PT is the progression of Pythagoras theorem. Actually, this is the right triangle COQ that is coming from the original domain. In this right triangle COQ, according to the Pythagoras theorem, CQ squared, that is the square of the hypotenuse, equals to CO squared plus OQ squared. So I'll write it down. This will be equation 1. So CQ squared, that is the square of the hypotenuse, is equal to CO squared plus QO squared. CO is X plus 5, therefore CO squared is X plus 5 squared. and it is equals to CO squared. CO is 5, therefore CO squared is 5 squared, that is 25, plus QO squared. So here, we subtract 25 from this equation, equation 1, and finally get that according to equation 1, QO squared equals to x plus 5 squared minus 25. In the next step, we will join points O and P together by a straight line. Point O is the center of this big quarter circle. Point P is the point of the big quarter circle itself. Therefore, PO is the radius of this big quarter circle. This is equals to 10 units in its length, according to what is given in the question. So PO equals to 10. PQ equals to X. It is the radius of this small quarter circle PQS. And QO is the missing side. So I'll copy the right angle PQO in the new page, and we will implement the Pythagoras theorem on this right angle PQO. Here by PT is the abbreviation for Pythagoras theorem. So actually this is the right angle PQO that the corresponding was knowing. In this right angle PQO, PO squared, that is the square of the hypotenuse, equals to PQ squared plus QO squared. So I write it down. This will be equation 2. According to equation 2, PO squared, that is the square of the hypotenuse, is equal to PQ squared plus QO squared. PO is 10, therefore PO squared is 10 squared, this is 100. And this equals to PQ squared. PQ is x, therefore PQ squared is x squared plus QO squared. So here we will subtract x squared from this equation, equation 2. Again, this goes into equation 2. QO squared equals to 100 plus x squared. So according to equation 2, QO squared equals to 100 minus x squared. Well, according to equation 1, we already found out that QO squared equals to x plus 5 squared minus 25. So we have two different equations for QO squared. Therefore, we will create the equation 3. It states that q all squared according to equation 1 must be equal to q all squared according to equation 2. Q all squared according to equation 1 is equal to x plus 5 squared minus 25. And it must be equal to q all squared according to equation 2. Q all squared according to equation 2 equals to 100 minus x squared. So in total, according to equation 3, we found out that x plus 5 squared minus 25 equals to 100 minus x squared. We open the brackets of this expression and we get that x plus 5 squared equals to x squared plus 5 squared, that is 25, plus 2 times x times 5, that is 10x, minus 25 equals to 100 minus x squared. So in this equation 3 we have 25 minus 25, that is 0. Now to represent 25, in this side of the equation 3 we left only with x squared plus 10x equals to 100 minus x squared. And again, according to equation 3, I should know that x squared plus 10x equals to 100 minus x squared. Here we add x squared to this equation 3. And finally get that according to equation 3, x squared plus x squared is 2x squared plus 10x equals to 100. Here we will subtract 100 from this equation 3, and finally get that according to this equation 3, 2x squared plus 10x minus 100 equals to 0. So here we will divide this equation 3 by 2, and finally get that according to equation 3, two x squared over 2 is x squared, plus 10x over 2 is 5 squared, so this plus 5. Again, 10x over 2 is 5x, so this is plus 5x, and minus 100 over 2 is minus 50. And it equals to 0 over 2 is 0. So in total, according to equation 3, I should find out that x squared plus 5x minus 50 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared plus 4 times a times c over 2a. In our specific quadratic equation, that is to say x squared plus 5x minus 50 equals to 0, the variable that we are looking for is x. X is the radius of this small quarter circle. So x is the number that we are looking for. The coefficient A equals to 1. The coefficient B equals to 5. And the coefficient C equals to minus 50. The only thing that is left to do is to put the data of our specific quadratic equation inside this general formula for x. This way we find out the value of the radius of x, that is the radius of the small quarter circle. So we'll do it now and get that x equals to minus b. B is 5, therefore minus b is minus 5, plus minus square root of b squared. B is 5, so b squared is 5 squared, that is 25. Minus 4 times a times c. Minus 4 times a is minus 4 times 1, that is minus 4. And minus 4 times c is minus 4 times minus 50, that is plus 200. So in total we found out that minus 4 times a times c is plus 200, divided by 2a. A is 1, so 2a is 2 times 1, that is 2. So in total we found out that x equals to minus 5 plus minus 4 of 25 plus 200 over 2. So x equals to minus 5 plus minus 25 plus 200 is 225 divided by 2. So in total, we found out that x equals to minus 5 plus minus square root of 200 over 2. So x equals to minus 5 plus minus the square root of 225 is 15 over 2. So here we have two solutions that are possible for x. The first solution for x is that x equals to minus 5 minus 15 over 2. Minus 5 minus 15 is minus 20, and minus 20 over 2 is minus 10. So according to the first solution for x, x equals to minus 10 units. But because of the fact that x is the length of the radius of this quarter circle, so x is a length, it must be a positive number. Minus 10 is a negative number, so therefore this solution is the correct solution. We can set the solution and we have only we take into account only the second solution for x. The second solution for x is that x equals to minus 5 plus 15 over 2. Minus 5 plus 15 is 10 and 10 over 2 is 5. So according to the second solution for x, x equals to 5 units in its length. That is to say, the radius of this small circle x equals to 5 units in its length. Our task is to find out the size of this shaded area. So what is the size of the shaded area? Or shaded region. And from the drawing, it is very easy to see that the size of this shaded area in total will be equal to the area of this big quarter circle AQB. minus the area of this semicircle minus the area of this small quarter circle PQS. Again, if you hold on the size of this shaded region into the shaded area, it was equal to the area of the big quarter circle AOB minus the area of the semicircle minus the area of the small quarter circle PQS. What is the area of this big quarter circle AOB? You know that the radius of this big quarter circle is 10, and therefore the area of the big quarter circle must be equal to pi r square over 4. So that is to say, this pi times 10 square over 4 minus the area of this semicircle. What is the area of this semicircle? Because of the fact that the radius of this semicircle is 5, it means that the area must be equal to pi r squared, that is pi 5 square over 2. So the area of this semicircle is equal to pi times 5 square over 2. Minus the area of this small quarter circle PQS. Because of the fact that we only found out that the radius of this small quarter circle x equals to 5, x equals to 5, therefore the area of this small quarter circle PQS must be equal to pi times 5 square over 4. So here we have pi times 10 square. 10 square is 100, so in total, in the numerator we have 100 pi so the numerator in total we have 100 pi over 4. If 5 square is 25, so in total in the numerator we have 25 pi over 2. So we multiply both the numerator of this expression by 2 in order to have a common factor if those two expressions. So 25 pi times 2 is minus 50 pi over 2 times 2 is 4. So in total we found out that the area of the semicircle equals to minus 50 pi over 4 minus the area of the small quarter circle PQS. The radius of the small quarter circle is 5, and therefore the area of the small quarter circle PQS must be equal to pi times 5 square over 4. So here we take out 4 as a common factor of those three expressions. We get that 100 pi minus 50 pi is 50 pi, and 50 pi cos 25 pi is 25 pi over 4. And 25 pi over 4 equals to 19.635 square units in size. Repeat again, we should find out that the size of this shaded region in total is equal to either 25 pi over 4 square units in size, or in terms of numbers is equal to 19.635 square units in size. So we finish with the first question. In the next step I present you the second question. So the second question of this lecture. The second question, our task is to find out the size of this shaded region. So in the drawing you have those two semicircles that intersect with each other at those 2 points. In addition, you know that AB equals to 5 units in its length. AB is the diameter of this semicircle, that is 5. This is angle ABC, this is equals to 15 degrees in its size. So first of all, we will divide drawing those two semicircles, we will divide them into 3 areas. We will define the size of this shaded area, that is the area that we are looking for in this question, as A. This is to say the shaded area equals to A units in A square units in size according to our definition. Likewise, we define this small semicircle as B. We define the intersection point between BC and this semicircle. This point is point M. And we define the size of this area AMB. Define the size of this area AMB as C. That is to say, it is equal to C square units in size according to our definition. It is given as a question that those two semicircles can go into each other, and therefore they are identical, and therefore they must have the same areas. So writing down, if we found out that the area of this semicircle AB is equal to the area of this semicircle CB. Again, because of the fact that those two semicircles can go into each other, we derive that they are identical, and therefore they must have also the same area. Only to equation 1, the area of semicircle AB equals to the area of semicircle CB. AB is the diameter of this semicircle. We define the center of this semicircle. This point is point O. So the diameter AB of this semicircle is equal to 5, and therefore the radius AO must be equal to 5 over 2. Likewise, the radius OB of this semicircle AB must be also equal to 5 over 2 units. In the next step, we will join points M and A together by a straight line. By joining points A and M, we can develop a triangle A and B. Triangle A and B subtend on AB the diameter of this semicircle, and therefore it must be equal to 90 degrees inside according to rule 7. So if we speak on rule 7, according to rule 7, if a peripheral angle subtend on the diameter of the circle, then it is equal to 90 degrees inside. In the drawing, we have a circle. This is peripheral angle ACB. That subtend on chord AB, that is the diameter of this circle, and therefore it must be equal to 90 degrees inside according to this rule 7. So according to rule 7, any peripheral angle that subtend on the diameter of the circle must be equal to 90 degrees inside. So, as I already mentioned before, we have peripheral angle A and B that subtend on AB, that is the diameter of this semicircle, and therefore it must be equal to 90 degrees inside according to rule 7. In the next step, we'll do a construction, that is to say, from this point M, we'll do perpendicular on AB. Again, from point M, we'll do perpendicular on AB. So okay, this angle equals to 90 degrees inside, and this angle also equals to 90 degrees inside according to our construction. We define the touching point of the perpendicular from point M and AB. This point is point Z. We define the length of MZ. We define the length of perpendicular MZ as H. In the next step, we calculate the area of this right triangle A and B in two different methods, and then we carry the equation 1 that states that the area of this right triangle A and B according to the first calculation must be equal to the area of this same right triangle A and B according to the second method of calculation. So I'll copy the right triangle A and B in an equation. We calculate the area of this right triangle A and B by using two different methods. is given us a question that AB equals to 5, it is the diameter of this semicircle AB. Here by PT is the relation for Pythagoras theorem. So actually, this is the right triangle A and B, that the common from the other domain. So, the area of this triangle A and B, according to the first method of calculation, is equals to the base AB times the height edge over 2. So the area of the right triangle A and B equals to the base AB times the height edge over 2. In the next step, we will calculate the area of this side and B in a different way. The area of this side and B must be equal to the base AM times the height MB over 2. So the area of the right MB equals to the base AM times the height that is MB over 2. So in equation 1 we have AB times edge. AB is 5 times edge over 2 and is equals to AM times MB over 2. So here we have 2 on both sides of this equation, so 2 will get cancelled, or we multiply this equation by 2, and this way we eliminate 2. Get according to equation 1, 5 H equals to AM times MB. Okay, 5H equals to AM times MB. In the next step, I'll copy the right triangle A and B again in a new page, and we analyze this right triangle A and B. And in order to find out the length of side AM and the length of side MB. Okay, in equation 1 we have 5H equals to AM times MB. So we have to find out the value of AM and MB. So 3, this is right triangle A and B, this is the curvature from the original drawing, this right triangle A and B, sinus 15 degrees equals to AM over AB. So sinus 15 degrees is equal to AM over AB. AB is 5, so substitute AB by 5 in this equation, and we get that sinus 15 degrees equals to AB over 5. Here we will multiply this equation by 5, and we get that 5 times sinus 15 degrees equals to AM, or AM equals to 5 times sinus 15 degrees. We're going to focus on this right triangle A and B, on this right triangle A and B. Cosine 15 degrees is equal to MB over AB. So cosine 15 degrees is equal to MB over AB. AB is 5. Here we multiply this equation by 5 and find again that MB equals to 5 times cosine 15 degrees. When we already found out that AM equals to 5 times sinus 15 degrees. Repeat again. We found out that MB equals to 5 times cosine 15 degrees, while AM equals to 5 times sinus 15 degrees. According to equation 1, we already found out that 5H equals to AM times MB. H equals to AM times MB. So now we can substitute AM in equation 1 by 5 times sinus 15 degrees, and substitute MB in equation 1 by 5 times cosine 15 degrees. And we get that 5H equals to AM. AM is 5 times sinus 15 degrees plus MB. MB is 5 times cosine 15 degrees. So to that, we should found out that H equals to 5 times sinus 15 degrees times 5 times cosine 15 degrees. Here we will divide this equation 1 by 5 and find again that H equals to we have 5 times 5, so only 5 will be left after we divided the equation by 5. We get here that it is equals to 5 times sinus 15 degrees times cosine 15 degrees. And again, according to equation 1, we should find out that h equals to 5 times sinus 15 degrees times cosine 15 degrees. This is according to equation 1. So here we have the trigonometric identity. It states that sinus 2a equals to 2 times sinus a times cosine a. Here we divide this equation, this trigonometric identity by 2. And we get that sinus 2a over 2 equals to sinus a times cosine a. And again, if we found out that sinus 2a over 2 equals to sinus a times cosine a. So, according to this trigonometric identity, we find out the value of sinus 15 degrees times cosine 15 degrees. According to equation 1, we just found out that h equals to 5 times sinus 15 degrees times cosine 15 degrees. What is the value of sinus 15 degrees times cosine 15 degrees? According to this trigonometric identity, sinus a times cosine a equals to sinus 2a over 2. And therefore sinus 15 degrees times cosine 15 degrees will be equal to sinus 2 times 15 degrees, that is 30 degrees over 2. So in total we found out that sinus 15 degrees times cosine 15 degrees, according to this trigonometric identity, is equals to sinus 40 degrees over 2. So in total we found out that h equals to 5 over 2 times sinus 40 degrees. Sinus 40 degrees is 1 half. So in total we found out that h equals to 5 over 2 times 2, that is 4. So h equals to 5 quarters units in its length. H equals to 5 quarters units in its length. Because of the fact that those two semicircles can go into each other, they must have also the same areas. Again, because of the fact that those two semicircles AB can go into semicircle CB, they must have also the same areas. So you can write down that they have this semicircle AB is equal to the area of semicircle CB. What is the area of this semicircle AB? Semicircle AB consists of those two shapes. And therefore, the area of semicircle AB must be equal to the sum of the areas of those two shapes that it consists of. That is to say, it must be equal to B plus C. And again, the area of semicircle AB must be equal to the sum of the areas of those two shapes that it consists of. That is to say, it must be equal to B plus C. So the area of semicircle AB equals to B plus C. And the area of semicircle AB equals to the area of this semicircle BC. What is the area of this semicircle BC? Semicircle BC consists of those two shapes, and therefore the area of semicircle BC must be the area of semicircle CB must be equal to the sum of the areas of those two shapes that it consists of. That is to say, it must be equal to A plus B. So the area of semicircle CB equals to A plus B. Maintenant, according to equation 1, we shall find out that B plus C equals to A plus B. Here we will subtract B from this equation 1. And finally get that according to equation 1, yeah, B will get cancelled. B on both sides of this equation, so B will get cancelled. And finally get that C equals to A. So this is shape ACB. This is equals to C square inside, and this is equals to the size of this shaded area. This is equals to A. So those two areas, they are equal to each other in their sizes. So A equals to C. So in order, our task is to find out the size of this shaded area, or the size of this shaded region. So we just have to find out the size of this area ABC, and because of the fact that C equals to A, the area of the shaded region will be equal to the area of this shape ABC, because A equals to C. So we find out the size of this area of this shape MBA or ABM. This shape A and B consists of two shapes, but before that we'll join points C and A, C all together by a straight line. By joining points C and O, we can do side triangle AOC. Side triangle AOC subset on chord AC. Likewise, we have here triangle ABC. This is triangle ABC that subset on the same chord called MA. Actually, triangle AOM subset on chord AM. Likewise, triangle ABM also subset on the same chord called AM. And because of the fact that those two angles are both subset on the same chord called AM, the size of this triangle must be equal to twice, it will be twice as large as the size of this triangle that subset on the same chord called AM, according to Rule 13. repeat rule 13. According to rule 13, a third triangle is twice as large as the triangle subtended on the same chord. In the drawing, we have a circle. This is triangle ACB that's subtended on chord AB, and it is equal to 30 degrees in its size. Likewise, we have third triangle AOB that's subtended on the same chord AB, and therefore, according to this rule 13, the size of this third triangle AOB is twice as large as the size of this triangle ACB that's subtended on the same chord AB. And because of the fact that the size of this triangle ACB is equal to theta, therefore the size of this third triangle AOB that's subtended on the same chord AB must be equal to 2 theta. So we can implement rule 13 in our drawing. Well, in our drawing, we have those two angles are both subtended on the same chord AM. The size of this triangle ABM is 15 degrees, and therefore the size of this triangle AOM that's subtended on the same chord AM must be equal to 15 times 2, that is 30 degrees. So in conclusion, I have found out that the size of triangle AOM equals to 30 degrees, according to rule 13. Actually, so as I mentioned before, A equals to C. Therefore, we find out the size of this shape A and B. It will be equal to the size of this shaded area, because A equals to C. So here, shape A and B consists of two smaller shapes. It consists of this sector AOM plus this triangle MOB. So the size of this shaded area will be equal to the area of this triangle MOB plus the area of this sector AOM. So as is known, repeat again. We already found out that A equals to C. The shaded area equals to A, and A equals to C. So we just have to find out the size of this shape ABC. This equals to C, and this will be the size of this shaded area because C equals to A. This shape ABM consists of two smaller shapes. It consists of this sector AOM plus this triangle MOB. Therefore, the size of this area ABM, shape ABM, total must be equal to the sum of those two shapes that it consists of. That is to say, it must be equal to the area of this sector AOM plus the area of this triangle MOB. So, the size of the shaded area or shaded region in total, it must be equal to the area of this sector AOM the out line above AOM is assigned for a sector within sector AOM plus the area of this triangle MOB. Repeat again. This is the shape AMB that equals to C, and C equals to A. We have to find out the value of A. but because of the fact that c equals to a, we just have to find out the value of this shape a and b. This is equals to c. This shape a and b consists of those two smaller shapes, and therefore in total the size of this shape a and b must be equal to the sum of those two shapes that it consists of. That is to say, it must be equal to the area of this sector AOM plus the area of this triangle MOB. Again, in total we should find out that the size of the shaded area is equal to the area of sector AOM plus the area of triangle MOB. Why? Because of the fact that shape A and B consists of those two smaller shapes. And therefore, in total, the area of shape A and B must be equal to the sum of the areas of those two shapes that it consists of. That is to say, it must be equal to the area of the first shape that it consists of, that is actually the area of sector AUM plus the area of triangle MOB. So this is sector AOM. What is a sector? A sector is a portion of a circle. The green shape AOB is a sector. It is a portion of this circle enclosed by two radii and RKB between them. Again, a sector is a portion of a circle enclosed by two radii and RKB between them. So a sector, it is like a slice of a pizza. And the area of this sector AOB equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is theta, over 360 degrees. Again, the two radii are defined as the legs of the sector. So in total, the area of this sector AOB must be equal to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is theta, over 360 degrees. So use this formula in order to find out the area of this sector AOB. According to the formula that I presented to you, the area of this sector AOB will be equal to pi r squared. R is the radius of this semicircle that contains the sector. This is pi r squared times the angle between the legs of the sector, that is 30 degrees, over 360 degrees. Repeat again, in total, the area of this sector AOM equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 30 degrees, over 360 degrees. So the area of sector AOM equals to pi r squared times 30 degrees over 360 degrees. R is the radius of this semicircle, is equals to 5 over 2. If r equals to 5 over 2, it means that r squared must be equal to 5 over 2 squared. So in total, pi r squared is equals to pi times 5 over 2 squared times 30 degrees over 360 degrees plus the area of this right triangle and the area of this triangle MOB. What is the area of this triangle MOB? It is equal to the base OB times the height of the base, that is h. The height h creates 90 degrees with the base BO. This is a right angle. So times the height, that is h, over 2. So in total, the area of this triangle MOB equals to the base BO times the height h over 2. And again, the area of triangle MOB equals to the base OB times the height h over 2. So we have here pi times 5 over 2 squared. 5 over 2 squared equals to 5 squared, that is 25, over 2 squared, that is 4, and we have to multiply it by 30 degrees over 360 degrees. 30 degrees over 360 degrees is 1 over 12. Plus OB times h over 2. OB is the radius of this semicircle, is equals to 5 halves times h. H equals to 5 quarters, so it is times 5 quarters divided by 2. So in total, we found out that the area of the shaded region equals to, here in the numerator we have pi times 25 or 25 pi over 4 times 12 is 48 plus in the numerator we have 5 times 5, that is 25 h equals to 5 quarters. It's 5 quarters. So in the numerator we have 2 times 2 is 4 and 4 times 4 is 16. So in total we found out that the size of the shaded region, the size of this shaded region, in total it is equals to 25 pi over 48 plus 25 over 16. In terms of numbers, it is equal to 3.2 square units inside. Equal to 3.2 square units inside. And again, we found out that the area that we also found this question, that is the area of this shaded region, in total it is equal to 3.2 square units inside. So finished with the second question. In the next step, I will start the lecture and start with the first question, of course. first question, our task is to find out the size of this shaded region, or the area of this shaded region. So in the drawing, we have, this is the big quarter circle AOB. Inside this big quarter circle AOB, we have a semicircle, and this is the small quarter circle PQS. Again, our task is to find out the area of this shaded region. We also know that AO equals to 10 units in itself. AO is the radius of this big quarter circle, equals to 10. Therefore, OB is also the radius of this big quarter circle, that equals to 10. AOB is a quarter circle, and therefore this is a right angle. Likewise, PQS is also a quarter circle, and therefore this is a right angle. So we have here this is the semicircle touch externally. This quarter circle is point M. So they have an external edge between them at point M, and therefore we can implement here rule 10. Rule 10, according to rule 10, if two circles touch each other externally, then the straight line that connects the circles together passes through their tangent point. In the drawing, we have those two circles that touch each other externally. This point, point P. The center of this circle is at point O. The center of this circle is at point M. The straight line that connects the circles together is of course the straight line OM. And according to this rule 10, the straight line OM must pass for their touching point, that is point P. Again, the straight line OM must pass for point P, that is their touching point. Or OPM is one straight line. Again, according to this rule 10, OPM is one straight line. So we can implement rule 10 in our drawing, because in our drawing, the semicircle touch this small quarter circle at point M. The center of this quarter circle is at point Q. The center of this semicircle is at point C. The straight line that connects the centers together is of course the straight line CQ. And according to rule 10, the straight line CQ must pass for point M, that is their touching point. Or CMQ is one straight line. If CMQ is one straight line, it means that CQ in total must be equal to CM plus MQ. So CQ equals to CM. CM is the radius of this semicircle, that is 5, plus MQ. MQ is the radius of this small quarter circle, that equals to X. So in total, CQ equals to X plus 5. CQ equals to X plus 5. In the next step, I copied the right triangle COQ in a new page and implemented the Pythagoras theorem on this right triangle COQ. This is the right triangle COQ that is according to the original drawing, according to the Pythagoras theorem. In a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this right triangle COQ, it means that CQ squared, that is the square of the hypotenuse, equals to CO squared plus QO squared. CO is x plus 5, therefore CO squared is x plus 5 squared, and it is equals to CO squared. CO is 5, therefore CO squared is 5 squared, is 25 plus QO squared. So in total, according to equation 1, we should find out that x plus 5 squared equals to 25 plus QO squared. Here we subtracted 25 from this equation 1, and finally found out that according to equation 1, QO squared equals to x plus 5 squared minus 25. In the next step, we join points P and O together by straight line. Point O is the center of this big quarter circle. Point P is the point of the big quarter circle itself. Therefore, PO is the radius of this quarter circle, that is equals to 10. In the next step, I copied the right triangle PQO in a new page and implemented the Pythagoras theorem on this right triangle PQO. So this is the right triangle PQO that is according to the original drawing. This right triangle PQO, according to the Pythagoras theorem, PO squared, that is the square of the hypotenuse, equals to PQ squared plus QO squared. PO is 10, therefore PO squared is 10 squared, that is 100, and this is equals to PQ squared. PQ is x, therefore PQ squared is x squared plus QO squared. So total, according to equation 2, we should find out that 100 equals to x squared plus QO squared. Here we subtracted x squared from this equation, and finally found out that q all square, according to equation 2, q all square equals to 100 minus x squared. When according to equation 1, we only found out that q all square equals to x plus 5 squared minus 25. So we have two different equations for q all square. Therefore, we can have equation 3 that says that q all square according to equation 1 must be equal to q all square according to equation 2. Q all square according to equation 1 equals to x plus 5 square minus 25, and it must be equal to q all square according to equation 2. Q all square according to equation 2 equals to 100 minus x square. So total according to equation 3, we found out that x plus 5 square minus 25 equals to 100 minus x square. Here we open the brackets of this expression and finally found out that according to equation 3, x plus 5 square equals to x square plus 5 square, that is 25, plus 2 times x times 5, that is 10x, and it is equals to minus 25, and it is equals to 100 minus x square. In this side of equation 3, we have 25 minus 25, that is 0. Also, we get 25, in this side of the equation, we have to leave with x squared plus 10x equals to 100 minus x squared. Here we added x squared to this equation 3, and we found out that x squared plus x squared is 2x squared, plus 10x equals to 100. Here we subtracted 100 from this equation 3, and we found out that according to equation 3, 2x squared plus 10x minus 100 equals to 0. Here we divided this equation 3 by 2, and found out that 2x squared over 2 is x squared, 10x over 2 is 5x, and minus 100 over 2 is minus 50, equals to 0 over 2 is 0. So total according to equation 3, we found out that x squared plus 5x minus 50 equals to 0. So actually, this is a quadratic equation, and the general formula for quadratic equation is ax squared plus bx plus c equals to 0. This general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say x squared plus 5x minus 50 equals to 0, the variable that we are looking for is x. X is the radius of this small quarter circle. The coefficient a equals to 1, the coefficient b equals to 5, and the coefficient c equals to minus 50. So the only thing that is left to do in order to find out the variable that we are looking for, that is x, is to put the data inside this general formula for x, and inside this general formula for x, and this way we find out the values of x. So we did it, and we found out that x equals to minus b. B is 5, so minus b is minus 5, plus minus square root of b squared. B is 5, so b squared is 5 squared, that is 25. Minus 4 times a times c. A is 1, so minus 4 times a is minus 4 times 1, that is minus 4 times c. C is minus 50, so minus 4 times minus 50 plus 200. Divided by 2a. A is 1, so 2a is 2 times 1, that is 2. So in total we found out that x equals to minus 5 plus minus 25 plus 200 is 225 divided by 2. So we found out that x equals to minus 5 plus minus square root of 225 over 2. So x equals to minus 5 plus minus the square root of 225 is 15 over 2. So here we have two solutions that are possible for x. The first solution for x is that x equals to minus 5 minus 15 over 2. Minus 5 minus 15 is minus 20, and minus 20 over 2 is minus 10. So if you found out that x equals to minus 10 units, but because of the fact that x is the length of this small, the radius of this small quarter circle PQS, x is a length, it must be a positive number. X cannot be equal to minus 10, it is a negative number, so we cancel the solution and take into account only the second solution for x. The second solution for x is that x equals to minus 5 plus 15 over 2. Minus 5 plus 15 is 10 over 2, and 10 over 2 is 5. So if you found out that x equals to 5 units in its length, that is to say the radius of this small quarter circle PQS equals to 5. Our task is to find out the size of this shaded region. From the drawing it is very easy to see that the size of this shaded region equals to the area of the big quarter circle A or B minus the area of this semicircle minus the area of this small quarter circle PQS. Repeat again, the size of the area of the shaded region must be equal to the area of the big quarter circle AOB minus the area of the semicircle minus the area of the small quarter circle PQS. The radius of this big quarter circle AOB is 10, the area of the big quarter circle must be equal to pi r square over 4. R is 10, so it is pi times 10 square over 2. Pi times 10 square over 4. Minus the area of the semicircle. The radius of the semicircle is 5, and therefore the area must be equal to pi times 5 square over 2. Minus the area of this small quarter circle, PQS. The radius is 5, and therefore the area must be equal to pi times 5 square over 4. Here we multiplied both the numerator and the denominator of this expression by 2. 25 pi times 2 is 50 pi, and 2 times 2 is 4. So in total, this expression equals to 50 pi over 4. So the area of the shaded region equals to 100 pi over 4 minus 50 pi over 4 minus 25 pi over 4. We took 4 second factor of those three expressions. 100 pi minus 50 pi is 50 pi, and 50 pi minus 25 pi is 25 pi over 4. So if you found out that the area that we are looking for this equation, that is the area of this shaded region, in total it is equal to either 25 pi over 4 square inches in size, or in terms of numbers it is equal to 19.635 square inches in size. So I finished to repeat on the first question. In the next step I repeat on the solution of the second question. In the second question, our task is to find out the area of this shaded region. So in the drawing we have two identical circles that intersect with each other at those 2 points. We know that AB equals to 10, that is to say the diameter of this semicircle AB equals to 10, and therefore the radius must be equal to 10 over 2, that is 5 over 2. Again, the radius, the diameter of this semicircle AB is 5, and therefore the radius must be equal to 5 over 2. So the radius AO is 5 over 2. The radius OB of this semicircle is also 5 over 2, 5 halves. Because of the fact that those two semicircles can go into each other, they must have also the same areas. That is to say, the area of semicircle AB must be equal to the area of semicircle CB. In the next step, we join points A and M together by straight line. We join points O and M together by straight line. And from point M, we do perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the length of MZ as H. By joining points A and C, we created peripheral angle A and B. Peripheral angle A and B subtend on AB, that is the diameter of this semicircle, and according to Rule 7, any peripheral angle that subtend on the diameter of the circle or semicircle must be equal to 90 degrees in size. Therefore, peripheral angle A and B must be equal to 90 degrees in size according to Rule 7. In the next step, I copied the right triangle A and B in a new page, and we calculated the area of this right triangle in two different methods, and then we created equation 1 that says that the area of this triangle A and B, according to the first method, must be equal to the area of the same triangle A and B, according to the second method. So this is the right triangle A and B that according to the original drawing. And Z equals to H according to our definition. So the area of this triangle A and B according to the first method, it is equal to the base AB times the height H over 2. According to the first method, the area of this triangle A and B equals to the base AB times the height H over 2. And according to the second method, the area of this triangle A and B must be equal to the base AM times the height MB over 2. Then we get the equation 1 that says that the area of triangle A and B according to the first method must be equal to the area of triangle A and B according to the second method. Here we have 2 on both sides of this equation, so 2 will get cancelled. After we cancel 2, we should find out that AB is 5, so in total here we have 5H equals to AM times MB. Here 2 will get cancelled. So in total we should find out that 5H equals to AM times MB. What is the value of AM and MB? In order to find out the value of AM and MB, I commit the triangle A and B in a new page. Analyze this triangle A and B. So this is triangle A and B, this is the formula from the original domain. This triangle A and B, sinus 15 degrees equals to AM over AB. Again, sinus 15 degrees equals to AM over AB. AB is the hypotenuse. AB is the hypotenuse, that is 5. So sinus 15 degrees equals to AM over AB. AB is 5. So substitute AB by 5. So in total we should find out that sinus 15 degrees equals to AM over 5. Here we must multiply this expression by 5 and finally found out that AM, the means inside AM, is equal to 5 times sinus 15 degrees. Likewise, in this right triangle A and B, cosine 15 degrees equals to MB over AB. So cosine 15 degrees equals to MB over AB. AB is 5. So in total cosine 15 degrees equals to MB over 5. Here we multiply this equation by 5 and found out that MB equals to 5 times cosine 15 degrees. Well, we already found out that AM equals to 5 times sinus 15 degrees. We already found out that according to equation 1, we already found out that 5H equals to AM times MB. But we just right now found out that AM equals to 5 times sinus 15 degrees and MB equals to 5 times sinus cosine 15 degrees. So in total, we should find out that 5H equals to 5 times sinus 15 degrees times 5 times cosine 15 degrees. Here we divide this equation 1 by 5 and found out that H equals to, here we have 5 times 5, so 1 5 will get cancelled because we divide this equation by 5. So in total we should find out that H, according to equation 1, H equals to 5 times sinus 15 degrees times cosine 15 degrees. Here we have the geometric identity that says that sinus 2A equals to 2 sine A times cosine A. Here we divided this geometric identity by 2 and found out that sinus 2A over 2 equals to sinus A times cosine A. So we use this geometric identity in order to find out the value of sinus 15 degrees times cosine 15 degrees. According to equation 1, H equals to 5. And we have sinus 15 degrees times cosine 15 degrees. According to this geometric identity, we get that sinus 15 degrees times cosine 15 degrees equals to sinus 2A over 2. That is to say, it is equals to sinus 2 times 15 over 2. So it is equals to sinus 2 times 15, that is 13 degrees over 2. So in total, sinus 15 degrees times cosine 15 degrees equals to sinus 15 degrees over 2 according to this geometric identity. So in total, according to equation 1, we found out that H equals to 5 times sinus 15 degrees over 2. So H equals to 5 over 2 and sinus 15 degrees is 1/2. So in total, we found out that H equals to 5 over 2 times 2, that is 4. So H equals to 5 quarters units in itself. This is Z equals to H and H equals to 5 quarters units in its length. Because of the fact that those two semicircles can go into each other, they must have also the same areas. That is to say, the area of semicircle AB must be equal to the area of semicircle CB because they can go into each other. What is the area of this semicircle AB? Semicircle AB consists of those two shapes. Therefore, the area of semicircle AB must be equal to the sum of the areas of those two shapes that it consists of. That is to C must be equal to B plus C. And again, the area of semicircle AB in total must be equal to B plus C, that is the sum of the areas of the two shapes that is consists of. And it is equal to the area of this triangle and the area of this semicircle CB. What is the area of this semicircle CB? Semicircle CB consists of those two shapes. And therefore the area of semicircle AB, the area of this semicircle CB must be equal to the sum of the areas of those two shapes that it consists of. That is to say, it must be equal to A plus B. So now we found out that the area of semicircle CB must be equal to the sum of the areas of the two shapes that it consists of. That is to say, it is equal to A plus B. So in total, according to equation 1, we actually found out that B plus C equals to A plus B. Here we subtracted B from this equation, and finally found out that C equals to A. A is the area of this shaded region, so we found out the area of the shaded region equals to the area of this shape A and B. And because of the fact that those two areas are equal to each other, in order to find out the area of this shaded region, we just have to find out the area of this shape A and B. So, by joining points O and M together by a straight line, you can deduce straight triangle AOM. This is straight triangle AOM. Straight triangle AOM subtend on chord MA. Likewise, we have peritriangle ABC that subtend on the same chord called AM. And because of the fact that those two areas are both subtend on the same chord called AM, the size of this straight triangle AOM must be twice as large of this as the size of this peritriangle ABC. The size of this peritriangle ABC is 15, and therefore the size of this triangle AOM must be equal to 15 times 2, that is 30 degrees, according to all 13. So the size of this triangle AOM equals to 30 degrees in its size. So we found out that the size of this shaded region, or the area of this shaded region, equals to the area of this shape A and B. So we just have to find out the area of this shape A and B. This will be equal to the area of this shaded region. And this shape A and B consists of those two shapes, those two smaller shapes. This is the first shape that it consists of, that is actually sector AOM, plus the area of the second shape that it consists of, that is actually the area of triangle MOB. Repeat again. The shaded region, the area of the shaded region equals to the area of this shape A and B. So we have to find out the area of shape A and B. It will be equal to the area of this shaded region. Shape A and B consists of those two smaller shapes. The first shape that it consists of is actually sector AOM, plus the second shape that it consists of, that is actually triangle MOB. So in total, we found out that the area of the shaded region must be equal to the area of the first shape that it consists of, that is actually the area of sector AOM, plus the area of the second shape that it consists of, that is actually the area of triangle MOB. So, repeat again, what is a sector? A sector is a portion of a circle. The green shape AOB is a sector which is a portion of this circle enclosed by two radii and RKB between them. The two radii are defined as the legs of the sector. The area of this sector AOB is equals to pi r squared. This is the area of the circle that contains the sector times the angle between the legs of the circle that is theta over 360 degrees. Repeat again, the area of this sector AOB must be equal to pi r squared times the angle between the legs of the circle that is theta over 360 degrees. And therefore the area of this sector AOC must be equal to pi r squared. R is the radius of this semicircle that contains the sector, times the angle between the legs of the sector that is 30 degrees or 360 degrees. And again, if you found out that in total, the area of sector AOM equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector that is 30 degrees or 360 degrees. R is 5 halves, therefore r squared is 5 halves squared. So pi r squared is pi times 5 half squared times 30 degrees over 360 degrees. Plus the area of the second shape that shape A and B consists of. The second shape is the area of this triangle COB. What is the area of this triangle COB? It is equal to the base OB times the height edge over 2. So the area of triangle COB equals to the base OB times the height edge over 2. OB is 5 halves and height is 5 quarters divided by 2. Here we have 5 over 2 squared is 5 squared, that is 25, over 2 squared, that is 4. So in total, in order we have 25 pi over 4, and we have 30 degrees over 360 degrees, that is 1 over 12. So in total, the value of this expression in total is equal to 25 pi over 4 times 12, that is 48. This expression in total equals to 25 pi over 48 plus 25 over 16. So in total, we should know that the area of this shaded region is equal to either 25 pi plus 48, 25 pi over 48 plus 25 over 16 square root in size. So in terms of numbers, the size of the area of this shaded region is equal to 3.2 square root in size. Okay, thank you very much.